Hi, thanks for tuning in on this presentation reference weather compensation. So, why weather compensation? Throughout the heating season, we tend to do the following in our homes. So Monday night, we set the lounge temperature to 21 degrees. Tuesday night, we set the lounge temperature to 21 degrees. Wednesday night, we set the lounge temperature to 21 degrees. You can start to see a trend. The only variable in the equation is the outside temperature. This is where weather compensation steps in. The lower you run the system water temperature, the more efficient your heating is to run, saving you money. So the aim of this presentation is to take you through a definition of weather compensation, a brief overview of heat loss, a brief overview of radiator outputs, types of weather compensation, how it works and how it's set up, the room influence, getting away from out-of-date technology, a working example and summary. So definition of weather compensation. Definition of weather compensation can generally be taken to describe a control function that maintains internal temperatures by varying the flow temperature from the heat generator relative to the measured outside temperature, i.e. the warmer it is outside, the lower the flow temperature and that of the heat emitters, while still maintaining comfort conditions. So heat loss. Okay, there's always a design outside temperature. The below temperatures are up to 50 meters above sea level. So Scotland and the islands, we'd be designing to -5. Midlands and Wales, we'd design to -3 outside temperature. Southern England, because it's down in the tropics, -1 outside temperature. We design outside temperature of -3 due to our location with the internal temperature changing for rooms. So 21 for our lounge, bedrooms 18, and this is all dictated by the Domestic Heating Design Guide, which I'll call SIBSE for short because that's who produce it. So here's our heat loss, and as you can see, our aspect A on our wall is at -3 outside temperature because it's got an external wall. And we've got an inside temperature of 21, which is a 24 degree difference. We've got our U value, and we've also got our area, meters squared, of wall. You've also got the glazing, -3 outside, 24 degree delta because it's 21 inside, and then the heat loss, which is taken from the U values and everything else. So you've got your fabric loss, your ventilation loss, giving you a total heat loss for the room. And if you note 21 and 21 here, this is an internal wall, so there's no heat loss to an internal wall inside the property unless you start shutting all your radiators off and everything else. Alright, so this is a lounge 21 degrees. So the big factor to take into account is design outside temperature of -3. Average winter temperatures in the UK are 9 degrees C. Heat loss will change as the outside temperature changes. So if it is 3 degrees outside and 21 inside, we have a 24 degree difference in that temperature. We can now take our heat loss from our room or building and divide it by 24, so that the heat loss calculation I just showed you for that room, 24 degree difference, we can take that figure and divide it by 24. So 1051 watts divided by 24 equals 43.8 watts per Kelvin, or degree change of outside temperature. So if it's 9 degrees outside and 21 inside, we have a 12 degree difference. So we can now take our watts per Kelvin or per degree, times that by 12, and now that gives us a new heat loss of 525.6 watts at 9 degrees outside temperature. So it's halved. Okay, so if we go to this room sheet here, you can see on the left hand side I've got all of the outside temperatures. The inside temperature is going to stay the same, it's going to be 21, and we've got a delta between the two all the way changing and our watts required. Okay, so we need 1051 watts to heat the room at -3 outside. Divide that by 24 gives us 43.8 watts per Kelvin. And as you can see, at 9 degrees outside, we've got a 12 degree difference, times that by 43.8 gives us 525.5 watts of energy required to heat the house at 9 degrees outside. And it's the same for the whole property heat loss. So we've got an 8 kilowatt load here. Okay, so it means per degree change outside we need 333.3 degrees. So you can see at 9 degrees outside our heat loss is actually halved. We only need 4 kilowatts now. So radiator output, and have a look at our radiator sizing presentation so you understand radiator sizes. But if we were going to pick a radiator for that room at our design temperature of 50, or mean water to air temperature, we'll pick a 600 by 600 K2, 1067 watts output from that radiator. Okay, by sizing to -3 outside temp, at 9 degrees outside temp, we're putting double the amount of energy into the room to heat it. We could control this 3 ways. So first of all, we could change the radiators in the room for every time the temperature outside changes to match the heat loss. This is very impractical and not cost effective. 2 is use a thermostat to limit the temperature in the room. However, this is causing cycling and still puts too much energy into the room. Or 3, we could be sensible and use weather compensation. So option 1 is just daft. We're not going to have 24 different sets of radiators in our property or invest in the labour to mess about changing them. And bear in mind, it doesn't change every day, it changes multiple times in the day, the outside temperature. Option 2 is the equivalent of this. Okay, that emphasises it. You're just racing towards the red light. You're still putting too much energy in if you're sticking to one flow and using a thermostat. So by changing the temperature of the flow using weather compensation into the radiator, we can now reduce the output from the radiator, matching our heat loss at different outside temperatures. So at -3 outside, okay, the outside temperature, we've got the inside temperature, we've got the delta between it, and then we've got the watts required. We need 1051 watts. So as we change to 5 degrees outside, we only need 700 watts. And at 12 degrees outside temperature, we only need 394 watts. So you can see, as that outside temperature changes and varies, we need less input from the radiator, or output from the radiator, into the room. So our watts required here, we've got -1, so we need that wattage. So by lowering the flow temperature, I'll just go through this one. So we've got the watts required, the flow temperature, the mean water temperature of the radiator, and then the watts output, or the rad output. And you can see more of this on our radiator sizing video. Okay, so we can see our actual watts required is this. By lowering the flow temperature, we've now reduced our mean water temperature, which has reduced our radiator output to almost match what we're losing. Same with this, 9 degrees outside, you can see the wattage required. You can see by lowering the flow, we've actually decreased the output of the radiator, matching what we're losing. And same again, at 13 degrees outside, we only need 350 watts to heat the room. So by lowering the flow to 52 degrees, we've lowered the mean water temperature, which has now lowered the radiator output. Bear in mind this DT sort of, or mean water to air temperature, sizing at 50 with a flow of 81 and a return of 61. It won't condense. We're only going to start condensing when we start getting into this sort of realm here. Okay, so the bigger the radiators and the lower the design temp, the more condensing you'll get on the actual boiler itself. So what we're doing, we're trying to balance our heat loss with our actual inputs into the property, as opposed to racing towards red lights. So types of weather compensation, is a basic and there's an advanced. So the basic would be like 2018 Wiesmann 100. You get a number of different curve options, but all you're doing is you're changing the level of the curve. Okay. So select one curve only, there's no setback temperatures, and the curve just produces one room temperature. So if you've got curve set for 21 degrees in the room, if you set your thermostat to 18, for example, it's still going to be putting enough energy into the room to try and raise the temperature to 21 degrees. So you're putting too much in just to be killed by a thermostat. So advanced weather compensation, you can see now if we want a room temperature of 22 degrees or 12 degrees, we're actually, the software is controlling this. with the use of setbacks, so a setback of 22 and setback of 12. The curve changes the control setback temperature and times. So if you want it 18 degrees at night to sleep, you just lower the setback and it's closed loop control. So you can see, if I want the room to be 21 degrees, at 0 degrees outside I'm going to have a flow of 69. But if I wanted it to be 12 degrees, it would actually step the curve down lower to accommodate that and then give me a flow of 40 degrees. So the system design temperature will determine what level the curve is set to. Lower design temperatures, which is all to do with your radiator sizing, and like things like air source heat pumps would operate at a lower temperature. The lower the curve you'll operate your system at, and the more efficiency you'll actually gain. Okay, so how it works and how we set it up. So changing the flow according to the outside temperature. So if it's cold outside, it's going to be a hotter flow. If it's warmer outside, it's going to be a cooler flow temperature going to the radiators. You need a boiler with a software and weather compensation capability. You just install an outside sensor on the north or the west side of the building via a cable back to the boiler. Sensor is usually an NTC thermistor. Viessmann tend to use a 10K NTC thermistor, which changes the resistance according to the temperature. The boiler uses this resistance to interpret the outside temperature and adjust the flow as per the set curve within the internal software. Some internet controllers advertise weather compensation in a loose sense. They tend to take an average of 3 weather stations via the internet, and it's not very accurate because they're doing this, because you've got internet data coming in, and the weather station could be up to 15 miles away from your actual property location. So weather compensation reacts far quicker than than adjusting a thermostat, as it's already adjusting the flow to the actual external changes outside. Okay, so you can see here we've got a boiler at 19 degrees. So what we've done is we put a set point on our boiler to the desired room temperature. This works best on colder days, and then we just adjust the curve to the room temperature on the boiler app or the actual internal software of the boiler itself. So we're looking to match what you've asked for on the boiler to what the room temperature is at. Okay, if the temperature is too low compared to the set point, you'd raise the curve, and vice versa. If it's too high, you'd lower the curve. So room influence. In some scenarios, we may need room influence. So this comes in the form of a thermostat. This would be used as a limiter. So if the temperature gets above 22 degrees, for example, the boiler would turn off. It'd break the link back to the boiler, the switch live. This would be required when there's lots of solar gain is experienced at the property, as the software does not know it's above the set point inside the property. It's just pumping away as you've told it to for the curve on a cold day. In effect, what you've done is you've reintroduced another heat source influencing the property. Your solar gain would be a little bit like having a log burner in the property. It's going to shoot over temperature because you've got far too much energy going in there. Okay, this is seen on mostly cold sunny days, so it could be really cold outside, so that the sensor has been picking up a cold temperature, the boiler's putting out a certain flow, but then you're getting a load of sun coming in through the windows and heating the property up. So getting away from out-of-date technology. So S-plans, which is a type of wiring system and control system. Y-plans, similar. Okay, so the hot water, if you had a cylinder and a boiler, the hot water has to be heated to 60 degrees for regulations. A minimum flow of 65 is usually required to achieve this, because you're never going to heat a cylinder to 60 degrees with a flow of 30. You are then forced to have your radiators at the same temperature. This puts far too much energy into the room for your heating on most days, causing overshoots in temperature and cycling of the boiler. Bear in mind, average temperature is 9 degrees outside, and it's -3 probably 1% of the time. So you don't need that flow temperature going through your radiators. Again, you're just racing towards red lights. So by controlling it in this way, you're losing efficiency. Alright, so we used to add additional kilowatts to the heat loading for the property when we were sizing a boiler for hot water. However, we tend to use priority domestic hot water these days. So the benefits of this is we get a smaller boiler, we get dual temperature system and weather compensation on the heating. And also the cylinder it's charged up, but it's got a thermistor in the cylinder as well, so the boiler can actually see the rate of change and start ramping it down, as opposed to just being stopped dead by a 230 switch live thermostat. Okay, so because I have an 11 kilowatt boiler and cylinder with a 16 kilowatt coil, I'm actually getting my hot water in my house to condense through 95% of the heat up. My heating is also range rated to a maximum heat loss of 6 kilowatts. So not only am I getting dual temperature, I'm also getting dual value in my heat output from the actual boiler itself. We've got Intergas, which do an X plan, which again is priority domestic hot water. But this is now getting run on open term. It's not so much using the weather compensation. So it's away from pure weather compensation and it's more load compensation. So this might be good for a property where you want it to pick up your temperature relatively quickly. Like say you're out most of the day and you get home, you might say, well, we'll go for open therm because you'll have a quicker heat up time of the property. You don't just need to maintain the property. Thermostats that do this are like things like Nests, not Hive, Nest I'd say, and like other Honeywell products. Just because you've got a Nest doesn't mean you're operating on open therm. First of all, you need the boiler to have an open therm capability, and you need it to be wired the correct way so the open therm is controlling the boiler. The thermostat starts to see the rate of change in temperature in the room, and that starts to modulate the boiler, as opposed to the boiler just getting a 230 switch live and trying to control itself on flow and return temperatures. So lots of people have these Y plans and S plans, and they've got a cylinder thermostat like this, bimetallic strip to control the hot water. So it was invented in 1759. I think we can do better than this these days. We don't need to be using all of this super old technology, because it's just going to be switch live 230, suddenly it's going to stop, which means you're going to overshoot and the boiler's going to have too much energy and everything else in there. So I'm not against them for heating limiters, they do a job, but I don't think we should be controlling hot water these days on them. So working examples and the summary. So this is an install we've done. We've got a 4-pipe priority domestic hot water Wiesmann 19 kilowatt boiler here on a holiday let. So fitted a 4-pipe on an LPG on a holiday let, so LPG is quite expensive. The client was worried that the guests would just leave the heating on max, so by setting the correct curve on the weather compensation, we were able to have a max heating temperature of 21 degrees. So the thermostat in effect could be set to 32 degrees C. The thermostat was then just a limiter in this scenario, and the curve determined the room temperature, not the thermostat itself or guests coming in whacking it up and going because they're not paying for the gas. Okay, so in summary, Wiesmann studies have shown a 15% reduction in energy use with weather compensation. I think they've actually shown more than that, and you can get extra efficiencies out of the system. You're only ever matching the heat loss for the actual outside temperature. Greater comfort, efficiency, and lower ongoing maintenance costs because you're running at lower temperature. You're not putting as much stress on the whole system. Lower corrosion rates and everything else. It's greener for the environment, and you're targeting room temperature, not radiator temperature. I say this again, you're targeting room temperature, not radiator temperature. If we've got Jim down the road and he's had a back boiler, so his radiators like take the skin off your hand when you touch them, and they were coming out like 85 degrees, I could go and fit a weather compensated system for him, and although the room is at 21 degrees, he might be ringing me a lot until he gains the understanding of it's the actual room temperature we're targeting, because he's going to touch the radiators, they're going to be lukewarm, and he's going to say that boiler's rubbish, I don't get any heat from it. And it's not that. We're targeting room temperature, not radiator temperature. Alright, thanks for listening, and stay tuned for further content. Bye for now.